So let's talk about the confidence intervals now. The point estimators in simulation should better be estimated based on averages of m independent replications. So if you want to make a nice and efficient output analysis, you do not use a single replication of a system. You use multiple replications. So you increase the number of replications, which means, for example, if you are running a terminating simulation that belongs at single day, you are going to replicate that single day many different times. So let's just say number of replications is indicated by n. And these are going to be independent replications. Why? Because these replications are going to use different random number sequences. In each replication, you get different random number sequences, therefore different random variates for the input models. Therefore, the outputs are going to be independent from each other. Now, let's just say we have observed a discrete time output data. Let's just say we are talking about the time spent in the system by each entity. So this is my first replication. Y11 means the system time of the first entity in my first replication. Y12 means the system time of my second entity in the first replication, so on and so forth. And Y1N1 is what? It is the system time of the entity number N1 in the first replication. And in the first replication, if we take the average of the time spent in the system by all entities, that is going to be indicated by y bar 1 point. So there's a point here, which means this average is taken across the data within the replication. So the second index is a dot here. If you see it, if you look carefully, you will see it, which means that that average is taking across the data within this replication. And the first index shows that this is the average of the discrete time data obtained within this replication only. How did we calculate that average? So we have changed the entity index from 1 to n1 because we have observed n1 entities in the first replication. And we have summed them up and divided the total number of entities, and we have calculated the average within the replication. Now we are going to do the same for the second replication as well. You see the first index here changes to 2, just like here. So that is the average taken within the replication, and this average is the average time spent by the entities in the system, and it is changing from 1 to n2. You see in the second replication, we may have different number of entities. So on and so forth. For m replications, we continue like this. In the last replication, we may have an m entities here. And we are taking again an average for the time spent in the system for entities within that replication. And we have within replication averages. So these averages are called within replication averages. Now, if you take the average of the within replication averages, so this time you are going to run a summation over index I, and I is going to change from 1 to n, and you are going to sum up these values and divide them to m. So that average is going to be average across replications. Average of the averages. Average across replications means average of the averages. And that final average is going to be the estimate for the average time spent in the system. And that estimate, of course, is not equal to theta. It is an estimate based on a random sample, right? Because, I mean, if you have used a different random number sequence in these replications, in all of them, then you would have calculated a different theta hat value. Therefore, this is a statistical estimate. Therefore, we need to measure the error of this estimate with a confidence interval. And how do we calculate that confidence interval? Now, let's just say you have your sample obtained within each replication. So you have the replication average in the first replication, replication average in the second replication, so on and so forth. So this is your sample. The averages obtained from your replications are your sample values. We are not interested in the variance of the time spent in the system within a replication because these values are dependent with each other. The time spent in the system by each entity in the same replication should be dependent on each other. So therefore, we are not interested in the variance or the standard deviation coming within the replication. I am only interested in the variance coming across the replications, because the replications are independent from each other. Therefore, the analysis is going to be much more smooth here. So you know y1 dot is the average time spent in the system in the first replication. That is the average time spent in the second replication. And this ym dot is the average time spent in the last replication. These are independent from each other, and the sample variance across these independent replications is obtained like this. This is the variance formula. And here you see we take the average across replications, which is y bar. If you remember, y bar is the average across replications. And we calculate the squared deviation of the replication averages from the average across replications, or the overall average, and sum them up and divide it to m-1. Why are we dividing to m-1? To get a unbiased variance, right? Now, average within replications may not follow normal distribution. Even though we are summing up these values and taking these averages, these average within replications may not follow normal distribution. Remember the central limit theorem. What does central limit theorem say? It says, if you take the average of sufficiently large number of independent random variables, then that average should be normally distributed. The central limit theorem says that if you take the average of a sufficiently large number of independent variables, then their average should be normally distributed. Now here we have sufficiently large number of entities within a replication, but they are not independent. These time values, the time spent by each entity, they are not independent. Even if you take the average of them, that may not be normally distributed because they are not independent. However, the replications are independent. If you take the average across replications, then their average should be normally distributed if the number of replications is sufficiently large. This is why we need replications, my friends, because the average value within the data may not be normally distributed because the values are dependent on each other. However, the replications are independent, therefore the average across replications, which is y bar, most probably normally distributed if the number of replications is large enough. So because of that reason, according to the central limit theorem, the average across replications may follow normal distributions due to the independence. Therefore, because I know that this average across replications is normally distributed, I can provide a confidence interval to that by using t distribution, t quantiles. So once I calculate the sample variance across replications, so the sample variance of these values, remember, and y bar value, I can write a 95% confidence interval, or 100 times 1 minus alpha percent confidence interval, by multiplying the standard error. So this is called the standard error, standard deviation, which is the square root of the sample variance, divided by the square root of the number of replications, and we multiply that standard error with what? T quantile, and the degrees of freedom is going to be, of course, m-1, the number of replications minus 1, as you can see here. And if I subtract and add this value, this is called the half width. If I subtract and add this value to my average estimate, then this confidence interval is going to provide me a confidence level for my true estimate. True expected value. Okay. Now, if you increase the number of replications, you can easily see that if the number of replications m goes to infinity, that part is going to go to 0, right? But in which order? I mean, for example, if you increase the number of replications by multiplying it with 100, then the confidence interval is going to be narrow by 10, right? It is going to be narrower by 10. So if you increase the number of replications by multiplying it with 100, or in other words, if you use a 100 times larger number of replications, your confidence interval is just going to be 10 times smaller because of the square root there. So it's not a good way, because increasing the number of replications by 100 is going to mean you are going to wait for the results for an amount of time which is 100 times more. So it is increasing the accuracy of your estimates. However, it's a brute force way because the accuracy is not increasing as fast as the amount of time you spent for the simulation. This means you are going to wait for the simulation run to be complete for an amount of time which is 100 times more long. And even if you wait like that, you are going to get only a 10 times narrower confidence interval. So the accuracy is going to increase by the number of replications. However, it is not going to be as efficient as you expected. Now, we also have prediction intervals, and we need to introduce the difference between the confidence interval and prediction interval. A confidence interval gives us a 95% confidence level interval for the expected value that we are interested in. So this interval contains the true expected value of the performance metric with a 95% confidence level. I mean, even though the true expected value, for example, if we are interested in the average waiting time in the system, even if we are interested in that statistic, we also are interested in the possible values for time spent in the system. Not just the expected value, we are also interested in the distribution of that. Prediction interval bounds the average queue waiting time on any day. A confidence interval bounds the location of expected queue waiting times on certain confidence level. So we are going to study the confidence interval and the prediction interval in this example. So let's just say we have the average queue waiting time given in minutes for 5 replications or 5 days of a queuing simulation model. So these replications are independent from each other, and we have run that simulation with 5 days, 5 replications, and in each of the replications, the average queue waiting time is calculated as 7.33, 6.43, so and so forth by the client. Now, the question asks me to provide a 95% confidence interval for the expected queue waiting time. Now, in order to give the most reliable or most accurate result for the expected queue waiting time, I need to take the average across the replications, and that average is 6.708. Of course, you see there is a variance between the days. Even though I estimate the expected queue waiting time, that is just going to be the expectation. In some of the days, we are going to see long queues. In some of the days, we may be able to see very, very short queues. Therefore, the queue waiting times may change from day to day. For example, by chance, on any day, there may be a customer which requires a very, very long service duration, and that is going to affect the waiting times of every customer behind that certain customer. And in that case, the queue waiting times on that days are going to have an average which is large. For example, just like 7.33 here. So the prediction interval is providing me boundaries for the prediction that I'm going to make for any day, not the average of days. So confidence interval gives a prediction for the average of the days, but prediction interval gives an interval for the average within days. Okay, so we compute the sample mean by taking the average of these 5 observations, which is 6.7 approximately. And the sample variance coming from these 5 observations can be obtained by taking the differences of the replication averages from the average across replications. So this is called the deviation of the sample observations from the overall mean. And when we square it and divide it to 4, we get the sample variance, and the sample standard deviation is 0.489. Now, if we assume that the replications are independent from each other, and we need to assume that because they use different random number sequences, we can build a confidence interval for the expected queue waiting time with a 95% confidence level by adding and subtracting the standard error multiplied with the t quantile. the T quantile, if we check the T table, the T quantile for 4 degrees of freedom and 0.025 tail probability is 2.78, which is a lot larger than 1.96, which is the 97.5% quantile of the normal distribution, if you remember. So because the number of replications is very low here and the degrees of freedom parameter is low, we need to use the T quantile here. However, from statistics, you know that if the number of observations in your sample is sufficiently large, for example, if it is larger than 50, you can safely use the Z quantiles, not T quantiles, but Z quantiles you obtain from the standard normal distribution. Because in that case, when the degrees of freedom parameter is large for the T distribution, then these T quantiles are going to converge to Z quantiles. Now we check that from our table, and the sample standard deviation is divided by the square root of the number of replications, and that interval gives me a confidence interval for the expected Q waiting time. So we are predicting the average Q waiting time here, and if you increase your number of replications from 5 to, let's just say, 5 million, if you do that, then you are going to get a narrower confidence interval which has the lower bound and the upper bound values very close to each other. So the length of this interval may converge to 0 by the number of replications. However, the prediction interval gives me a 95% interval for the daily average Q waiting times to be in this interval. So we can say that in 95% of the days, the daily Q waiting time averages are going to be in this interval. If the expected value is reliable enough, this is going to be true. But there is also an error coming from the statistical estimation. So this 1 over 5, if it converges to 0 by increasing the number of replications, then we can surely say that this interval will cover the average Q waiting time in 95% of the days. Only 5% of the days are going to show an average Q waiting time which is either larger or smaller than the upper bound and the lower bound values respectively. So the only difference here is what? Instead of multiplying the standard deviation with square root of 1 over number of replications, we multiply the standard deviation with the square root of 1 plus 1 over number of replications.